Hello everybody, I'm Lilanka Kankanamge from National Building Research Organization, Sri Lanka. So today I'm going to present a case study on improving the performance of Badulusirigama Landslide using subsurface terrains. So in my presentation, I will cover the details about the investigation program and design of the rectification measures and also the evaluation of the performance of rectification measures at Badulusirigama Landslide. So let me give an outline to my presentation. Firstly, I'm going to give a brief introduction about the landslides in Sri Lanka, then an overview of the study area, then the site investigation program at Badulusirigama, then the assessment of the stability of Badulusirigama slope under different cases, then the conclusions of my study, then the references, and finally the acknowledgement. So when discussed about the landslide in Sri Lanka, the main focal point is the Central Highlands because as you can see, the figure shows the distribution of landslides in Central Highlands in the year 1994 and in 2018. So you could see the number of cases reported have increased during past 25 to 30 years. So these slopes in Central Highlands have altitude about approximately about 1,000 meters from the mean sea level. And these slopes are formed of colluvium and residual materials. And most of the time, the groundwater table is found well below the ground surface level, and the shallow depths remains unsaturated. But during the rainfall events, the progressing magnetic fronts could increase the saturation levels, leading to slope instabilities. When some features like relic joints and fractured rocks are present, the infiltration of water deeper into the slope would cause the rise in groundwater table, and it can eventually activate comparatively deeper slip surfaces. So when rectifying or mitigating these slopes, the main focus should be to control the rise of groundwater table and to direct the water paths away from the slope body. So in view of this, surface and subsurface drainage improvement have been widely used in Sri Lanka, and rectification of Butterworth landslide in 1992 and Nihalakot in 2016 are some of the major events that have been rectified using such drainage measures. So moving on to the case study, Badulusirigama is a small village located in the Badulla district in the Uva province of Sri Lanka. This landslide is comparatively larger with a length of about 500 meters and a width of about 120 meters. And initially the movements have been recorded in the year 2007, 2011, and 2012. This slip surface was encountered between the boundary of the topmost colluvium layer and underlying completely to highly weathered rock layer. And the depth to the slip surface from the existing ground level was about 10 to 12 meters on average. So to obtain further information about the landslide, a comprehensive site investigation program was conducted, inclusive of geomorphological surveys, borehole surveys, and geographical surveys. The figure shows the boundary of the landslide indicated in a dotted line and the borehole locations as well as the resistivity survey lines. And based on the investigation data, the subsurface profile of the site was established, which composed of three main layers: the topmost colluvium, completely to highly weathered rock, and the moderately weathered rock layer. And the sliding mass was divided into three slides: the upper slide, the middle slide, and the lower slide. And using the data obtained from the site investigation program, the three subsurface layers identified were assigned with the parameters shown in the table 1. When assigning parameters for subsoil layers, the result of the SPT test conducted at the site were used, and as well as they were adjusted based on the similar studies conducted in the past. And when performing the numerical analysis of the slope, initially the groundwater table profiles were established using the CW module, and then the stability of the slides were investigated using the slope W profile, slope W module available in GeoStudio software. So you can see the factor of safety values obtained for all the three slides are closer to 1, which indicates they have marginal safety. Marginal safety factors under the existing conditions. So the rectification design was conducted based on the site investigation data and as well as the initial numerical analysis conducted. And when designing the rectification measures, the main focus was to control the rise of groundwater table and to eliminate the development of perch water table conditions. So in view of that, surface and subsurface drainage measures were proposed. Altogether, 51 number of subsurface drains were built, which were arranged in fan type structure as shown in figure A, and they were installed at different elevations as shown in figure B. So this slide summarizes the simulation of subsurface drainage improvement in a 2D cross section. When simulating drains, bottom-up construction sequence was adopted, and a 3-day elapsed time was maintained during the installation of each drain, just to reflect the construction time required for installation of drains. So this slide summarizes the improvement or the gain of factor of safety in 3 slides. So we can see the middle and the lower slides has the factor of safety of middle and the lower slides have improved rapidly with the installation of first 2 to 3 drains, and the factor of safety of the upper slide has only started to improve with the installation of the drain B. So then the rectified slope with subsurface drainage measures was evaluated for an actual rainfall case. This is to investigate the adequacy of the installed drainage measures to maintain the stability during an actual rainfall event. So in view of that, an actual rainfall event was selected, which was occurred during December 2014. The figure 9 shows the variation of the factor of safety of 3 slides with the rainfall event. So a significant drop of the factor of safety of the 3 slide was noticed after the heavy rainfall event of 216 millimeter. The recorded minimum factor of safeties with the rainfall event were 1.16, 1.38, and 1.58 for upper, middle, and lower slides, respectively. The recorded FOS values are still greater than the previous factor of safety values, which were obtained for full saturated conditions without subsurface drainage measures. However, it should be noted that the analysis only account for subsurface drains, but the site has also the surface drainage measures installed. So the actual factor of safety values would have been higher than this. So the slope should have adequate safety margins during this critical rainfall limit. So with that, I'm moving on to conclusions. The results of the numerical analysis conducted shows that the subsurface drainage measures are effective in drawing down high initial water tables. With the installation of drains, in a bottom-up sequence, the safety margins of the slip surfaces increased gradually. There was a reduction of the factor of safety on all 3 potential failure surfaces when the critical rainfall event was applied on the rectified slope. In preceding days, the reduction of factor of safety was minimal due to the drainage of the infiltrated water through the system of installed drains. However, no significant rise of groundwater table was recorded during this rainfall event. The reduced factor of safety values of all three potential failure surfaces recovered gradually after the cessation of the rainfall. The effectiveness of a system of subsurface drains in maintaining adequate safety margins in a slope during prolonged high-intensity rainfall events is illustrated by this finding. So with that, I'm going to wind up my presentation. So these are some of the references that I referred using this study. And I would like to acknowledge my supervisor, Professor S.A.S. Kulathilaka of University of Moratuwa, Associate Professor Jyotisankasa of KU Thailand, and all the lecturers of the MINCH program, NBRO, and Geotechnical Engineering Division of University of Moratuwa, Sri Lanka. Thank you.